afternoon to everyone. Thanks for coming back from lunch in time. Thanks, Paola, for giving me the opportunity to introduce this section and presenting some recent challenges that has kind of bothered my life in the last few years. Of course, I want to start with the giving credits, because nowadays science cannot be done alone anymore. There is no space for Leonardo da Vinci. We are always, you need a team if you want to really push the boundary of science. And some of this team, as I think that for you is, there's Alex, Kostya, Dan, they are very known in our community. Giacomo just started his journey to academia, and I'm sure that he will be very successful. But I think that too often we forget that behind every successful experiment, there are the golden hand of a technician. And therefore, I just want to make sure that everybody knows that without Raphael and his magic hand, we would not be here. I would not be here for sure. So what I will do today, and try to be fast so people can rush to other section, I want to give you two case studies. One will be a single crystal X-ray diffraction. I'm a diffraction person. On a aluminium bearing bridgmanite, and the other will be a single crystal beryllium scattering. Both of these experiments are done at high pressure and high temperature. And although nowadays everybody thinks, oh, what is challenging there? I can really tell you that it's still very challenging to try to get good data at high pressure and high temperature simultaneously. We, in these last 30 years since I started my work, I hope you'll hear, right? The limit have been pushed really high, both in a diamond anvil cell, with resistive theater, with laser heating, both in a multi-anvil technique, which really reach now really very high pressure and temperature. The problem is that if you are, like my friend called me, a single crystal person, then you get into trouble, because most of the study can be done not easily, but they can be done with powder, with polycrystalline material. If you want to use a single crystal, then you go back a bit and say, what can I do? And that's what I want to try to show you today. So let's start with the first case study. I'm dealing since years and years with bridgmanite. Although it seems like kind of boring, this is one of the most important minerals of the lower mantle. So if we can really understand what chemical substitution, what temperature and pressure does to this structure, then we have an opening up of what is the structure of our deep earth. So as you can see, I just reported, I have to get them out. So I reported the structure, very simple, perovskite type structure, where you have magnesium in this big cavity and silicon on the octahedral side. And you have this nice framework that are distorted. We already heard about perovskite at the beginning of the week. What's happening is that, of course, in the Earth, this cation can be substituted. And what we were interested in was a particular substitution, the one of aluminum. Because aluminum is a trivalent cation, so you can have two different kinds of mechanisms in the substitution. And one, it will be the couple substitution, where you have a aluminum going to the octahedral side at the place of silicon, and one aluminum replacing magnesium at the big cavity. However, you can even have some place in the mantle, what is called oxygen vacancy mechanism. So you substitute only silicon on the octahedral side, and you create an oxygen vacancy in order to charge balance. And then this is the bromelairite type structure, which doesn't exist in the lower mantle, but it's just to show you what you may expect when you just do this kind of oxygen vacancy substitution. So what we were after is, of course, you have these two mechanisms. Which one is important when? That's what we want to understand. And is it really, they are really so different? Can we see the difference in the structure when we do these two different substitutions? Because unfortunately, they appear simultaneously. So you cannot have just only one of the two when you try to synthesize your sample. So Giacomo synthesized quite a few samples. No, sorry. Oh, I forgot, because I cannot see. So we wanted, of course, to do that at high pressure and at temperature. And this was starting to be the first problem, because you have a lot of possibility at synchrotron nowadays, where they tell you, like, for example, in this case, this is SRF, this is Petra 3, that they have this very nice resistive oven that goes quite high in temperature. And this is done with this kind of resistive oven. This is just a graphite foil that you crush between your between your diamond. And the problem is that you need a vacuum chamber, because if not, you want to avoid all oxidation of all your material because you are going at very, very high temperature. And then the only thing that I could find so far, maybe you are more experienced than me, I don't know, is that, for example, this graphite heater was used with a single crystal. They went up to 10 GPa and 900 K. The problem was that they used silicon oil as a pressure transmitting medium. Now, it's true that when you use silicon oil, is very non-hydrostatic. It's true that when you use a very high temperature, you relax the stresses, so it's not a problem. But if you try to put a small crystal of bridgmanite into this cell with silicon oil, you cannot heat it up at 2-3 GPa. You have to reach at least 20 GPa before heating. If not, you destroy your sample. And by 20 GPa, bridgmanite is amorphous in a non-hydrostatic medium. So for us, it was not a possibility. So what we decided to do is to try to use a very old design. This is actually a very old design of BGI, so many years ago. Leonid actually did it for the first time. This is just a platinum wire ceramic heater. So you have a piece of ceramic, you cut some slit, and you do a lot of turn of platinum wire. And then you put this one around the coulet, right? So you are heating the coulet and the diamond, both of them, of course, and your gasket. And then we asked Kostya if he could just do a very simple modification to the goniometer head that they use at Petra 3. So this is just their goniometer head, but you can see you have a ceramic insulator here. So there are two plates between the top and the bottom of this goniometer head. So what we do, we are cooling with water the lower part. We put our cell into a membrane that we also use to increase pressure. We flash some argon hydrogen flux in order to try to avoid oxidation as much as we can, but then we let that to get hot because we are trusting this lower part to keep cool everything else. So this part here will get quite hot. You can see it here. This is just a photo of the thing into the Petra 3 goniometer, where you see the camera of the Ruby system you put in and out so you can see your sample, and this is just the pinhole in the back. And this is our cell, which is heated with this platinum wire by passing current. Very simple. The nice thing about this is that we can use helium. So we can use helium as a pressure transmitting medium. So we don't have the problem on non-hydrostaticity at room temperature. And these are the samples that we use for this study that were synthesized by Giacomo in the multi-anvil BGI. And I would like to just to point your attention on the very small amount of aluminium we can have in there. Because what we want something representative of the lower mantle. And unfortunately, if you want to increase the number of oxygen vacancy in your sample, you need to have very, very low aluminium. You cannot have 20% of aluminium, it will be completely couple substitution. So what we were trying was to try to increase as much as possible this one, and this is pretty much the maximum 27 GPa. And then we wanted a sample that will add more or less the same amount of aluminium, but with majority of couple substitution. And this is why there are this very, very small variation. What I also want to show you is that, of course, this is a beautiful loading. And then when you start to compress and heat, we have helium, which is very, very soft. and therefore your gasket will just collapse and will be really deformed very much. Not only, but when you start to heat up, helium will become liquid again, because at those pressure, above 10 GPa is solid, but at higher temperature, it will become liquid again. And then you start to see moving your crystal. So it is really a game of, let's wait long enough until everything is stable, then we take a picture, then we center the cell, then we try to find the crystal, then we collect the data. However, I would like just to make you notice how beautiful are these data. I was really impressed. I mean, when I started my career, I thought I would never have been able to go so high in pressure and in temperature with a single crystal. And as everything in life, I was proved wrong, so it's fine with me. And then you can see, so this is at 3 GPa, 4 GPa. This is at 50 GPa room temperature. This is at 30 GPa and 950 Kelvin. And we still can see beautiful data. We could collect up to 350, 370 unique reflection, not total reflection, unique reflection. So we could do all the refinement in anisotropic, and we could have a discrepancy factor less than 3.5% for all our data, except in the crap one, but with that we threw it away. So these are the data. Apologies for the small thing. Oh, they don't look so small there. They look very small in the screen. What I normally like very large symbol, but here I wanted to put it small because you are dealing with a lot of uncertainties when you do this kind of experiment. So my way to see how good or bad are the data is to look at their scatter. So I'm not saying that our uncertainties are as small as the symbol. What I'm saying is that by making the symbol very small, I can see how bad they are. And if you notice, all the color code symbol, maybe I hope you notice, are actually well fitted by the line, which are just equation of state, PVT equation of state that we of course calculated, but you know, you could have much larger scatter. So I think that we really got very, very nice data. The population of data at high temperature is not that much, but you can imagine once that we reach that kind of hole, then either we stop the experiment or we break the diamond. And this is always depending how much money you have. I normally try, even at BGI, I still try to stop the experiment. So that's why we don't have so many high days, especially not at very high temperature, but they were enough to constrain all the EOS parameter of a Mie-Grunaisen equation of state with a Debye approximation, which are this line, okay? So once that I have that, so let's look at the real data. So first of all, what we see is that these are the two samples that we measured at high pressure and temperature. There are two more samples that we didn't have time. They don't give you much time at the synchrotron. You know, if you do one experiment, that's it. Then they say, now you have to write the paper and that's it. They don't say, oh no, you can do another composition and another composition, unfortunately. So this is the molar volume at room pressure and room temperature. And the first thing that we saw is that very likely all this major difference between oxygen vacancy mechanism and couple substitution mechanism that is present in the literature. They always say, oh, oxygen vacuum, you have much larger volume than the couple substitution, may not be so correct for the sample that are representative of the mantle. Of course, if I use brown millerite, I will probably have a very larger volume. But for this sample where the gain between oxygen vacancy and couple substitution is limited, we don't see this great difference, especially at this low concentration. Of course, if I extrapolate the two trends, I will have a much larger difference. But that's the other thing. I don't know if it's linear until the end member, and I don't care about the member because these one are the composition that we are interested in. That's the first observation. The second observation, of course, is also that the large difference that we're seeing in the bulk modulus, so in the compression of these two materials, is probably not there. There is some hint that, of course, your oxygen vacancy mechanism is a little more compressible than the couple substitution, but the difference is not as large as other studies were saying. At least that's what we think. All the other studies were done, of course, in powder, but they were done also quite a few years ago. So, you know, it's not that they are wrong. They did the best that they could with the technique of that time. It can be completely wrong, and in 20 years, somebody will tell you it's not true, but this is what we could do with the technique of today. So what we can do with all this data is, of course, we can forget about it, or we can say, okay, let's try to see if they make sense. And what Giacomo did was he just create a thermodynamic model which show how the couple substitution mechanism and the oxygen vacancy mechanism change as a function of pressure for a given aluminum content and a given temperature. And these were chosen simply because we have some experiment at those conditions. So we can compare it with experiment. So being experimentalist, we always want to compare with experiments, right? So what I wanted just to show, you don't have to look at all this detail. It's very complicated. I'm not going into the detail about how this model will be constructed. But what I want to show you is simply that this is our today model, which kind of fit the few very large uncertain data we have. This model here, which is with this dashed line, is based on the data on the EOS parameter that Schroeder reported in his compilation. So with all EOS parameters. And you can see that one was really missing, especially this middle point. So in the old days, when you had this major difference between the two mechanisms in terms of compressibility, you would have expected the oxygen vacancy mechanism to go down much more faster than it looks like it happens, okay? But being a crystallographer, I also cannot not to show some structural refinement. So all these compression mechanisms that are very minimal, we can see it because we did single crystal. We could see the distortion of our perovskite at all pressure and temperature. So what we see here, again, a bit complicated, but I hope that you will follow me. So you have the individual bond distances of the octahedral side. So you have the BO21 and BO22 are the basal bond distances. And then there is this BO1 that is the apical distances, which is the one along the C-axis. So in the case of MgSiO3, the M member, these are this black dashed line. You have a quite anisotropic compression, but the BO1, so the apical one, is practically identical to the longest BO2. And all the three distances start quite similar together. In the case of the aluminum substitution, what you have is that the one along the apical one gets really, really very much more compressible. So you have a difference between the basal and the apical one. Not only, but because we had this very good refinement, what you can see is that the blue symbol, which are the ones which are richer in oxygen vacancy, appears, maybe it's not true, but appears to be slightly more compressible. So what that will mean is that all of these small differences very likely are just simply due to the possibility of the aluminum to contract a bit its distances along the C-axis, which is the one that has just constructed this framing. Of course, we can also look at the tilting. You know, bridgmanite is a distorted structure from the cubic aristotype. So what we can see, we can just look at the movement of this tilting, which are here represented by this, what they call the airflow plus mode, which is that this displacement of the oxygen in this direction. So this is my out of phase tilting, right? And then the displacement of the oxygen in this direction along the C-axis, which is this M3 plus, which is my in-phase tilting. So if I look at this, these are the largest distortion of the bridgmanite structure. What I see is that for the couple substitution, the difference between the MgSiO3 and the and the couple substitution structure is not that large. The distortion is similar, although I'm replacing an aluminum in the A side and one in the octahedral side. But the distortion increase really seriously if I create an oxygen vacancy. This number seems very small, but it is, I'm displacing oxygen, so they are real, and I can see it because of the single crystal. Okay. The interesting thing, however, is, and I want you to, is that when we increase the temperature pressure, while the F4 plus, so I'm going back to be less distorted in this direction, my out-of-phase tilting gets better, gets smaller, because it's expanding. The M3 plus, independently of oxygen vacancy or whatever substitution, stay the same. It looks like this kind of movement is locked in, probably by the fact that this atom, which can be aluminum, magnesium, is actually moving closer to one side of the cavity while I'm compressing, and it has a better coordination if the M3 plus stay in place and doesn't relax again. So let's go to my second case studies, and I have still some time, I would say. So this is what we do with measurement of acoustic wave velocity. Lately, we are starting to try to measure acoustic wave velocity of different single crystals to try to get information on their aggregate property to model the Earth interior. So what we have at BGI, as you can see here, is we built a brilliant system already since quite a while, which can be used simultaneously with X-ray diffraction. This is the source of the X-ray diffraction. This is the diffractometer to measure density and velocity at the same time. However, that was always is possible only at room temperature. So what we have started to do in the last 5 years now, it's a long process and will not be possible without Alex. So we are trying to use a laser heating of our single crystal and measure velocity at temperature and pressure. The problem is that there are several problems, but one of them is that your samples are transparent, which means that you have to use CO2 laser. We are in Germany, so there is no way to mount a CO2 laser open and just use it. It is too dangerous. Nobody would be able to enter and not get burned because the radiation is invisible, so you don't know where it is, and is dangerous even if it's only diffuse. So I'm happy that I'm not allowed to have an open system there. So what we decide to try out is this articulated arm, which I don't know if it's visible, is a arm that they use in medicine. They're using medicine for cutting out your cystis or whatever. They really use it for CO2 laser heating. So it's really built for CO2 laser heating. So in this way, there are several mirrors in this junction. So the laser will be passed through all this arm and will arrive here, can you see, on the last junction and reach the diamond anvil cell here. And the free space is practically 2 centimeters. So it is really relatively as safe as it can be. Of course, if you burn a mirror and then also the junction, then you are, but we burn several mirrors, but we never succeed to burn the junction yet. So we are still safe. So when you do this, what you can do, you can therefore have your single crystal, and with the same, we can heat with a laser from one side, and we can measure brilliance at the same time. The problem starts that the sample preparation starts to become very complicated because you need to have, if you want to heat at high pressure, you need to use a lot of power. But with this arm, we cannot just use the 2-watt power of the laser. So we need to isolate our crystals between some isolation material, which is normally a salt. And you can see this. This is a nice crystal of KCl, I think. This crystal cannot just be picked up from the synthesis. They need to be usually, in this case, from the pyrope not, but usually if you have an isotopic material, it has to be oriented, double-side polished, down to possibly less than 10 micron. That's why Raphael is absolutely indispensable. And cut with the fib such that the dimension are exactly the dimension of your laser. Because what you want to do is to hit the whole crystal. You don't want to hit just a part of it, and then you will have cracks developing, and then you lose your nice surface, and then everything goes to, you have to start again practically. You cannot measure acoustic velocity if it is cut. So that's the way how we prepare it. And usually we try to put at least 3 crystals in there so that if one of them is burnt, and it happens more often than you think, then we can have another one to measure. At the same time, so we do brilliant, and from the same pinhole, we measure temperature, so the emissivity of the sample, because so we are sure that we are measuring the temperature where we are collecting the brilliant scattering. And then we measure pressure, because we discover after a while that it's true that the pressure doesn't change so much, but it changes. So if I want to try to get as accurate as possible data, I need to know what is the pressure at temperature. And the only way to do that is I cannot use the ruby, because everybody of you know that the luminance of ruby becomes a very large, broad feature when it's at temperature. So we are using the Samarian YAG, which is practically independent of temperature. If the YAG doesn't get warm because it's not heated by the laser. It's just in the same chamber, okay? So, and this is what it looks like, the experiment. So you have a nice, very bright pyrope. I forgot, we did pyrope not because pyrope is the lower mantle, most important mineral, but we needed something to benchmark our system because it's a new system. I don't want to start to have some very nice data and then start to think about a new model of the lower mantle without knowing that actually the data are correct. So this is my pyrope at 1900 K, plus minus 60, 70, maybe also 100, depending how well we can control that emission. And then these are the velocity, acoustic velocity measured at 20 GPa and the temperature of pyrope, VS and VP, so the shear wave and the longitudinal wave. And of course, the brilliant is dominated by your diamond, as usual, and in this case also by your sample, by your salt. So we have to collect for quite a long time to actually be able to see these velocities. But then you can see we could do quite a lot because we can increase pressure and we can increase temperature on the same crystal. And once that we find the laser, because we have first to find the laser, then we collected quite a lot of data. And one of the difference here is, for example, that we can collect high temperature data at relatively low pressure, which is important because in this way we can better constrain our room pressure equation of state parameter. So this line here again are all my fitting of the equation of state of a Mie-Gruneisen with the Debye model approximation of all our data. And then we didn't go much higher because anyway, it's pyrope. I didn't want to go to the lower mantle. The nice thing is that what we did then, because we don't have density, we are doing an iterative procedure. So I wanted to check that we were not going, when you have so many parameters, you can find a minimum that is completely wrong. So I wanted to check that our minimum kind of represented the data. So we calculate the volume expansion at room pressure, where we didn't measure our data. And you can see this is this black line, and this is in excellent agreement, I would say, with modern data of the volume expansion pyrope. Of course, this one here, you can see here, I put it here, is that calculated with the EOS parameter reported in this compilation of Stigsrud and Litvok Bertelloni, which is still based on all data of pyrope, as you can notice. So there is a major difference. And then, of course, you want to compare your data if you want to know if you are doing something wrong. And the only thing that I want to stress here is that if you look at the solid line, you can see that they fit better the data collected by Sinogenki at room pressure and high temperature. Then the model that we published with Chantel in 2016, which was based on data of multi-anvil, ultrasonic multi-anvil, which were collected only up here because we cannot collect at low pressure, because you need to close your sample in the multi-anvil and close all your crack and so on to have some proper ultrasonic data. So what's happened is that up here, the agreement between these two models is good because we had a lot of data also with Chantel. Down here is not so good because we were missing data and now we have it. And to conclude, so you can see here, I calculate the aggregate wave velocity of pyrope as a function of an adiabat. So here there is pressure, or every point is calculated at the temperature for that pressure of an adiabat, which is the one of Katsura, but you can use any adiabat you want. The thing is that I compare this one with the one from Chantel and from the one of Sticksrud. This is the model. It's not Sticksrud that he did it. It's just the model that the equation of state that are parameters that are written there in that compilation. And you can see that there is a large difference even at higher pressure. So, and Sticksrud, the old equation of state parameter are always underestimating the velocity. So when you read, if you are in our field, you will read a lot that the mineral physics model don't fit the PREM. So the seismic model, we are always a bit too low. And it could be simply because we were not able to sample enough high temperature. So from now on, if we can get much better data at high temperature, we may discover that this discrepancy is actually not there. And I just want to conclude with my future work, because challenges are what make life fun. So what we want to do now is, I like to create my small synchrotron at home. So now we will have a machine here that hopefully will be able to measure very small crystal, because getting time at SRS, or at Petra is not easy. So I'm going to do it at home. And this is actually Alex's arm that is mounting the arm. But what we want to mount is a detector so that we can measure density at high pressure temperature with PREM. Thank you.
Tiziana, very nice talk, very complicated data, not easy for us. Are there any questions?
Timmy.
So, do you think what temperature we can go heating helium with CO2? Because you showed heating up to 900 K.
Okay. So
I always heard that if you do that, the helium diffuses into the diamonds and then they explode.
Yeah, but the fact is that helium diffusing to the diamond if you already have some defect in the diamond. So I think that this diamond that we, with the Ballaran has done, are already much better. So we, with the resistive heater in helium, we heat it only up to 1000 K. And helium stayed in. What was happening is, unfortunate, is that because it's so soft, my gasket was the problem, not the diamond. The diamond break because the gasket break. So we didn't notice any helium escape. So if the helium escape outside and not into the diamond. So whenever we stop, before I said, okay, this is the last point, we always recover the diamond. With CO2, Alex tried something with, in collaboration with somebody from Oxford, and they succeed to hit something 1,400 K at 17 GPa, and it was in helium.
17
GPa, and it was helium. I don't know if it's a lucky thing because he did it once. No, he did it 3 times, and it didn't break. So the fact is that, I don't know, Leonid will say, no way, no helium. We need helium, so we do it.
Thank you very much. Very exciting result. And if I understand correctly, the elasticity as the temperature is underestimated previous data. So estimation of the temperature is really higher than current understand, or
What we mean is that, at least for pyro, I
Mm.
don't know if it's so.
Mm.
What we see is that the velocities are higher
Mm.
previously thought.
I
So,
see.
for
Mhm,
temperature,
mhm.
say pressure and temperature.
I see. So in order to match the mantle values, we need to go to higher temperature.
Yeah, the problem is that, for example, for garnet,
Mm.
sorry, I should stay here.
Mm.
Garnet is always a problem because they put your velocity down. So
Mm.
when you get a global model,
Mm.
your velocity are always lower. So
Ah.
Marta actually showed it in her thesis that we had too low velocities.
Mm, mm.
But if the high temperature, so if we are correct, those were underestimated. So we probably, this difference may be
Mm.
not so large.
I see.
Exactly.
Mhm. So how much is the difference? Real temperature
I mean,
is
this one for pyro, the problem is that I only have pyro,
Mm.
but in this pyro was, did you see it? So for example, it goes from 5, 6, 7. So from 9.7 in reality is almost 10.
Ah.
So it is significant. It's less than, it's more than the error. So my error is this line, so the color line. So it is more than that error.
Okay.
I mean, I'm comparing it with the 6th root, which was the one that has the compilation. If you already look at Chantel, the difference is just less. Of course, the compilation is with the data that are in the literature, but probably they're all data. Yeah, close.
Then how about the pressure scale? The pressure, assuming that the pressure is
So
quite
the
correct.
pressure scale, at the moment, as I said, we measure pressure with the R. So there is the error of the pressure, but we measure pressure at temperature. So it is at least consistent with the measurement we are doing.
Okay. Yes. Thank you very much.
Okay.
Posso? No?
He makes a comment later.
Tiziana, just a general question about the vacancy.
Okay.
If I well understand, the vacancy in perovskite increase the compressibility.
But just very small. They were in the literature. There is the increase in compressibility much larger than what we observe. But of course, we have very small amount of oxygen vacancy, which are actually the maximum you can get at 27 GPa, for example. You know, there is a really the variation of the oxygen vacancy with pressure goes up to 0.5, so this to 5%, down again at the top of the lower mantle. So there is not much oxygen vacancy at the moment. Of course, I'm talking about here, there is no water involved. There is, you know, for this kind of sample, this is the maximum amount that you can have.